Welcome back to my channel. Today I'm going to be talking about inverse equations. So an inverse equation is a normal equation, but it is reflected over x equals y, y equals x. So the xy point would move to the yx point. That's just how the tables would flip. So to find an inverse, you switch the x and y values in an equation. So y equals x squared would go to x equals y squared, and then you can solve for y and graph. So here's just an example table and graph. There is y equals x squared and x equals y squared, which is the same thing as saying y equals plus or minus root x. So the x and y, the table of y equals x squared is negative 2, 4, negative 1, 1, 0, 0, 1, 1, 2, 4. Just a couple of points I picked, and here is y equals x squared here. X equals y squared's table is 4, negative 2. If you see, these switch. So from negative 2, 4 to 4, negative 2. This works with all inverse equations. So negative 1, 1 goes to 1, negative 1. 0, 0 stays 0, 0. 1, 1 stays 1, 1. 2, 4 goes to 4, 2. So what we get here is we get this quadratic, but on its side. It's called a sleeping parabola. But as you can see here, this sleeping parabola does not pass a vertical line test, meaning it has two outputs for one input. So two y values for one x value. So really, you could take this half and keep it a function, or you could take this half and this half. So you'll erase one of these if you want it to stay a function, and then shaboom. You have a function now that is the inverse. And as you can see, this is reflected over the line y equals x. Let's keep going with them. So, some properties of inverse equations. So, the proper notation of the inverse of f of x is f to the negative 1 of x is proper notation. So, the domain and ranges will flip from this original. I just said the domain is x equals all real numbers, and the range is y is greater than 0. Well, then these will flip, and this inverse, the domain will be x is greater than 0, and the range will be y is all real numbers. Here are some example graphs of inverses. Excuse me. There is y equals root x and y equals x squared, but since here y is greater than or equal to 0, then that means x is greater than or equal to 0 on the y equals x squared graph. So we just keep 1/2. Then there's y equals b to the x in exponential, and y equals log base b of x. And you can see this is the exponential. This is the logarithm. The asymptote for the exponential is the x-axis. And since it's an inverse, it flips the domain and range. And the asymptote for the logarithmic function is now the y-axis. So, sometimes you may have to restrict the domain of a function to keep it a function, as we just saw with the quadratic, because it was not a function. It does not pass a vertical line test. So if there was a vertical line coming through these two arms, then if it hit 2 points, it's not a function. So you need a restriction on domain for functions that have inverses that do not qualify as functions. So the vertical line test. So here we have our quadratic, our sleeping parabola, and I put this vertical line through it, and it has 2 intersection points, meaning that it is not a function. They will require a domain restriction. So I can show you an example domain restriction. This is an example domain restriction. Excuse me. Y equals absolute value of x, and x equals absolute value of y. There is no way to get this in y equals form because there is no inverse of absolute value. As you will see here, there's a semi-inverse, but there's not a true inverse. So xy for y equals root x is just a quick table, -2, 2, -1, 1, 0, 0, 1, 1, 2, 2. Then we switch it here in this x equals absolute value of y. 2, -2, 1, -1, 0, 0, 1, 1, 2, 2. So, in this absolute value, an absolute value is the distance from the origin. So here we're saying the distance from 0. And you can't have a negative distance. As you see here, you plug in a -3 to root x, so absolute value -3 is 3. There's no way to get a negative absolute value. So these y values that are negative are not possible. So this down here, this is not possible. So you need a domain restriction that is y is greater than or equal to 0, because you cannot have a negative output of an absolute value function. So let's move on. The last thing we are doing is we are going to create an inverse. So create an inverse for y equals 1 plus root x plus 5. So first we are going to switch the x and y. So now we have x equals 1 plus root y plus 5. Then we're going to move the 1 over. X minus 1 equals root y plus 5. Then we are going to square it. So square both sides. Let me just show this step. So y plus 5 equals x minus 1 squared. And then y equals, move the 5 over, subtract 5 from both sides. So y equals x minus 1 squared minus 5. So if you see, I switched the x and y, I moved the 1 over, then I squared both sides to get rid of this absolute value here, because I want to isolate y and get it in y equals form. Then it's y plus 5 equals the squared of x minus 1, and then I move the 5 over by subtracting 5 from both sides, and y equals x minus 1 squared minus 5. So in this next equation, we're going to check that f of x and g of x are inverses. So if they are inverses, when you plug one equation in to the other as x, you should get x as an output. So f of g of x means we're plugging in g of x as the x value in f of x. So g of x is cube root x minus 1, and then that is cubed because of the f of x is cubed, plus 1. So then we just say, what is the cube root of x minus 1 cubed? Well, it's x minus 1, and then that's plus 1, and then we get x. So f of g of x gave us x, so that proves they're inverses, but we have to prove g of f of x too, just to be safe, I guess. So we're going to do the third root of x cubed plus 1 minus 1. So we just added that into g of x as x. Now, let's just simplify these ones. So the cube root of x cubed and the cube root of x cubed is x. So these two equations are inverses. I hope that helped. If you have anything else you would like me to talk about on this channel, please suggest it in the comments. Thank you for watching.